Okay, science time. That's how we start. I almost forgot. Science time. Today we are talking about science. Science, and we're talking about what is science. I'm going to, as I like to do but often forget, I'm going to write down the objective over here. And the objective today, as you can see on the board, is define science, cross-cutting concepts, and engineering practices. Define science. So please write this down. Define science, cross-cutting concepts. I'm going to put that in quotes because that's not like a word that we use in professional or adult science, but it is a phrase that we use in science education and engineering practices. So today we are defining science, cross-cutting concepts, and engineering practices. Tell me what science is. Someone, raise your hand and tell me what science is. Or to you, what is science? We've talked about this the first couple of days of school, but let's just kind of refresh our minds. What is science? Help me come up with, yeah, Chloe, what's up?
It's a process.
Okay, yeah, that is the specific word I was looking for. I'm also maybe on the lookout for a new marker, but my trash can isn't over there anymore, so. Oh, that was close. Process. Hopefully this marker will be better. What else is science? Thank you, Miss Pryor. That's really nice of you. You do not have to pick up the trash, but I'm glad that you did so no one slips. Yes, Avery. Finding a problem. Let me tell you, the older you get, the more you understand that you don't have to find problems. They will find you, I promise. Finding problems / making a solution. Yeah, I like that a lot. One thing I really like about both of these, does anyone else have something to add, or it's okay if you do. It's also okay if you don't. I think these are great. Amelia.
Like the study of something?
Yeah, a lot of times we work with the study of, etc. Right? Study of, like meteorology is the study of. It is not. It's the study of the weather. Meteorology is a study of the weather. Paleontology is a study of, not just dinosaurs and not just fossils, but of ancient life. Biology is a study of life in general. So really paleontology is kind of like a section of biology. But we talk a lot about these ologies. Ologies. Good luck with my handwriting, BT Dub. We're talking a lot about the study of something. Even in a way, something like psychology, the study of the mind, or anthropology, the study of people. In a way, those are sciences. And in fact, I shouldn't say in a way, that's kind of offensive to psychologists and anthropologists. Those are sciences. A lot of times we call them, and this is even more offensive, soft sciences, but those are sciences, and we're dealing with the study of various things. Most of these things are aspects of the natural world. In fact, science used to, in the past, be called natural philosophy, the philosophy of nature. Philosophy is a Greek word, or a word that comes from Greek, just meaning the love of knowledge or the love of wisdom. So natural philosophy is science. But I like these two especially, the process and finding a problem, making a solution, because it gets at the idea that science is not a body of knowledge only, it's a way of doing things. It's the way that we do things. It's a way of looking at the world where we, instead of just making assumptions or believing people, we analyze results and observe things and draw our own conclusions. And that's something like the scientific method. And that's what science kind of is based on, the scientific method. Have you heard of the scientific method before? Yes or no? Just do a little head nod or a short thumbs up. You have, I hope you've heard of the scientific method before. How many steps are in the scientific method?
A lot.
I like that answer. I really like that answer, Amelia, because I was hoping that someone maybe a little bit too dogmatic would say something like 6, like just straight up. There are 6. Like there are 10 commandments, there are 6 steps of the scientific method, or 5, because you could say either. But Amelia just says a lot, and there aren't really a lot. I'm going to posit to you that in my mind there are something like 3 steps of the scientific method that we do for almost all of science. Now, sometimes the door is open, but if both this door to the lab and the door that conjoins to Mr. O's room are open, you will see there's a poster on the back of that door that says the steps of the scientific method. And I think that one says there are 5. And now I'm saying there are 3. And so what, am I being blasphemous? I mean, no, my point is that there's a way that we can think about science, that there's not a set number of items in the scientific method. In general, the scientific method is comprised of we'll just put problem. And I'm going to give you an example that will hopefully lead you to understand that you do something like the scientific method all the time. Something like inductive reasoning, where you look at the things of the world and then will you check to see if that changed that, Tiana? Where you look at something in the world and then you analyze it. So a problem, and then we might find, I'll put analyze here, and conclude. So I'm going to give you an example that might help you realize that you do this a lot, that you do something like science. Maybe it's not in the strictest sense scientific research or scientific experimentation, or certainly not like a clinical trial, but it's something like science. So if you look outside with me, do you see that tree there? The near one, the one tree you can see most of. Does anyone not see that tree? If it was easier to readjust the camera, I would show the camera the tree, but it's not. The really good one, yeah. What kind of tree is that? Does anyone know what kind of tree this is right here in front of the window? Is this going to be a guess, or do you know, Amelia?
Oak.
Is that a guess, or do you know?
I know it's an oak.
It is an oak. You're right. But listen, there was a problem. What kind of tree is that? Is a problem. You don't have to write down that example. Maybe think of an example from your own life. I don't know what your life is like. Who's that cute boy across the gym? That's a problem in your own life, right? What's his number? That's a problem. You're doing this all the time in your daily life. What's for supper tonight? That's a problem. And then there's some kind of analysis. Now let me give you another example here. Does ibuprofen work to cure a headache? That's a problem. That's a problem. And how we analyze those things as a second step, maybe it does take the form of, like Mr. O's door, where it says, first we design an experiment, form a hypothesis, et cetera, or like we did in the lab, where we designed an apparatus, made a hypothesis about it. Maybe we do all the steps of what we would classically call a scientific method, but maybe it's as easy as we ask Amelia what kind of tree that is, and that's a kind of analysis. Maybe, realistically, if Amelia wasn't here, how would you find out what kind of tree that is?
Google.
Yes, exactly. That's what I was hoping you would say, because that's science, baby. That is what you are doing when you Google something that you don't know. What star is that in the sky? There's a thing called Google Sky Map where you can find out what star it is, and that's a way of looking at the world. It's a shortcut maybe, but it is still science, and then you form a conclusion. In the case of the oak tree, the conclusion is it's an oak tree. In the case of what's that girl's number? I don't know. Maybe it does conclude positive for you. Maybe it doesn't. I don't know. In the case of does the ibuprofen cure a headache, after the analysis, there might be literally years of clinical trials with very closely designated control groups and recipients of certain dosages. And so that in that kind of clinical trial, hard science, the analysis section might be very long. And the conclusion of that might be a scientific paper. But your conclusion is different depending on the rigor of the scientific method you're using. But in all of them, in my mind at least, in all of them, you are using these 3 things as a scientific method. Now, does that make the scientific method on the back of Mr. O's door, or that you learn in 6th grade, or that someone might learn at Shadron High School, if you're wrong? No, I don't think so. I think to me, these are just kind of the boiled down version of what we're doing when we're doing science in a way that makes you realize, or I hope helps you realize, that you do this all the time. That your way, kind of the standard way that people look at the world nowadays in modern America, is actually the scientific method. Because rewind 3,000 years and the problem of I guess what's that girl's phone number doesn't really make sense back then, but am I going to marry that girl when I grow up? The analyze might be like, well, let's cast lots or look at the liver of a chicken to figure out if the fates are in line with that. And that's not really science. But the way we do things now is effectively science. Like the modern Western culture way of doing things is basically science. And as we go through this book, you'll realize that we talk about a lot of things over and over and over again. Those are what I'm going to call, and what the NGSS and the Nebraska State Science Standards call, cross-cutting concepts. And we're going to talk about each of these individually, and we're going to do that with hopefully no more than 8 minutes. And that and then the science and engineering practices will be all we have time for today. And you will recognize very quickly that that is not everything that was in your text, but it is the stuff that I think is important that isn't in your text. Ideally, then, between your text and what we've learned today, you will have all the information you need to do a good job in this class. Okay, so the cross-cutting concepts are, and I'm not going to put these in any particular order other than the order in which they are on the poster, which I don't know who came up with that, but we have patterns. Would someone please read them to me? Patterns, cause and effect, scale, proportion, and quantity. Systems and system models. Energy and matter. Structure and function. End of list? Okay. I'm good at science. One, two, three, four, five, six. There are 6 cross-cutting concepts. These are called cross-cutting concepts because they are concepts, ideas, that cut across all different kinds of science. Basically, any kind of science, certainly any kind of hard science, and most of the soft sciences use these, will recognize these trends of information within them. Cool. Thanks. I'm not an idiot. I know how to count. There are 7 cross-cutting concepts. It's on YouTube forever now. But luckily, that's the only mistake I've ever made. So here you go, Tiana. You can have a certificate of mistake to make. No, that's not true. I'm not that full of myself. I know I make mistakes. If you ever find a video where I haven't made a mistake, maybe you'll get a ramrod for that one too. What's a pattern? Can someone tell me? For both of these, I'm not going to write down the example. I want a very brief definition in your words. Someone. I want a different person for each one, and then I want an example from someone else. Amelia, what's a pattern?
Like a repetition.
It might be repetitious. Yeah. Let's call it. Let's just call it a repeating sequence. I'm going to put a little like approximately repeating, because it doesn't have to be over and over and over and over and over and over and over again. It just has to be some kind of sequence that has a repetitious quality to it. We might. Oh, I was going to give an example, but I don't want to do that. I want someone else to give me an example of a pattern in science, in natural science. When I say natural science, I mean as opposed to like psychology or something, anthropology, soft science like that. I want from the natural sciences like biology or chemistry or physics, some familiar pattern that you see in those. Yes.
All mammals have hair.
All mammals have hair. Are there any exceptions to that?
We have hair.
Chloe says from under a pile of her own hair. A pattern. All mammals have hair. Do other organisms have hair?
Yes. Yeah.
Yeah. Well, caves. There's some differences of. It's not really opinion, is it? There's some differences of perceived factual knowledge. But yeah, all mammals have hair is a pattern. All mammals have hair. I can think of a tarantula. You have a tarantula, right, Isaiah? You should, because you seem like a tarantula haver. Tarantulas have hair. Now, it is morphologically, that means it is different in structure from mammals' hair, but it is usually considered hair. And so a repeating sequence, a pattern, the recurring element of hair in all mammals. Good. Cause and effect. Give me an example of cause and effect. Let's try to avoid biology for this one. We don't have them all be about biology. No, Amelia, you already went. You already went too, right?
Dang it.
I guess we ran out of people to answer questions even though there's like a jillion people. Teague.
Like they used to say, take responsibility for your actions.
Okay, that's
You did something and then you
okay.
get in trouble. You have to
I like that, a consequence. Mrs. Creech said this in a way that I think is nice and almost poetic, or maybe even beautiful. Mrs. Creech said, if you bring the librarian, just for the record, so that someone watching this in a few years might not know who Mrs. Creech is, I don't know, but if she said, if you bring back a damaged book, I'm not going to be mad, but you will pay for the book. There are still consequences, right? She doesn't have to be mad for there to be a consequence, but a consequence is because the book was ruined, the effect is you have to pay for it, right? Let's think of an example from science. Say it, someone who heard Avery, even though this doesn't really count as your own example. She didn't say it loud enough. Okay, Avery, let's hear it.
The dinosaur died, so we find his fossil.
Yeah, because the dinosaur died in a certain set of circumstances, we have found his fossil. Cause, death, effect, fossil. Does every dead organism fossilize? No, of course not. So it's not a strict one-to-one cause and effect, but that is a cause and effect. Scale, proportion, and quantity. What do these words mean? First of all, what's scale mean? How? Yeah, size. How big something is. Proportion, how big something is compared to other parts of it or of other things. And quantity, how? Yeah, someone said it. How many? How much or how many? Good. Give me an example of this from the natural sciences. I just put size there. Give me an example of that from the natural sciences. What's the biggest planet? Trap. What's the biggest planet in our solar system? Jupiter. That would be that knowledge is a cross-cutting concept. We talk about that in all different sciences, including astronomy. Systems and system models. What's a system? Not an example. We're not there yet. Okay. Yes. Yeah, I really like that one. I'm going to put it in quotes though, because sometimes when we say working, it makes it seem like they have agency, which many of the things, well, first of all, agency is kind of a philosophical principle. Maybe atoms do have agency. Who am I to say? But in the natural sciences, we usually consider that those inanimate objects are not capable of their own thought, and they're not working together like kids in a classroom, because you are capable of your own thought, at least most of you. But they are, these objects are interacting. Let's put that. They are interacting. Not just acting and reacting, but interacting. They are together acting. Give me an example of a system. Computer system. Good, yeah. Yep. Those are all different parts of a computer working together. Energy and matter, well, you should know what these are. Energy is change, and matter is stuff. Change and stuff. Structure and function?
Like a structure could be like a building.
Okay, yes. Structure could be like a building, yeah.
Function could be like what the building is.
Yeah, what it do. How it is, I'm going to put in quotes again, built. And then for the last one, the bell has rung, so I'll just write down the stability and change. That deals with change over time. You know, the differences we'll put, so we don't use the same word. Differences over time. We didn't have time to talk about the science and engineering practices, but my goal is to talk about those again before we do another lab. Questions before you go, or as you're going, I guess? Goodbye.